Hi everyone, the Sioux Falls physics teacher is back to look at a simple example of torque. We're going to be calculating the torque exerted on the fishing pole by a fish when the fishing pole is held at an angle. And again, remember that the key thing with finding torque is our equation of force times distance can only be used when the force is exerted perpendicularly. So here, our fish is attached out here at the end, so our total distance from the handle to the end has been given as 1.5 meters. But if we look at the force exerted by the fish, we see that that weight would be in the downwards direction. That is not perpendicular to the actual fishing pole itself. So in order for us to figure out exactly what the torque is, we're going to need to take this weight and break it into components. And again, we can kind of draw this diagram very similar to the way you would do a free body diagram on a ramp. One component of that weight is going to be going along the fishing pole. The other component of the weight, this one right here, is going to be going perpendicular. So we'll call this then the perpendicular component of weight, and that is the only component that will be used to calculate torque. To find that side then, again remember that when we're given our angle over here, that angle would be congruent to this angle here, and so our perpendicular component of weight is the adjacent side to our angle. So to find that component, we can set it up as the cosine of our angle is equal to the perpendicular component divided by the weight itself. And that means we have the cosine of 55 degrees is equal to the perpendicular component divided by the weight of the fish. And again, we want to put that in kilograms first. 0.85 kilograms multiplied times 9.8 will give us the weight of the fish. And we find that that component, again the part that is perpendicular to the pole, is only 4.8 newtons. Now we can go back to finding torque, and again our equation for torque is force times the lever arm or the distance. The component that is perpendicular is 4.8 newtons. Our distance is 1.5 meters. And notice that we still use the full 1.5 meters. That can be a little bit confusing because of how we've drawn our diagram. The fish, or the point where that force is attached, is still out at the end of the pole. So even though we're drawing this diagram to find this component that's here, that does not affect the distance that is used. So when we look at our final answer then, we do use the total 1.5 meters, and we end up with a torque of 7.2 Newton meters.
Okay, we have a problem here on torque again. Two masses this time are hung from a wheel, and we want to calculate the net torque that is exerted on that wheel. We have a 1 kilogram mass and a 0.5 kilogram mass. So let's tackle the 1 kilogram mass first. It is hanging at a 45-degree angle, so we need to figure out the torque that is going to provide to the wheel. In doing that, we're going to need to then consider this 1 kilogram mass being hung here. off the edge of the wheel. We know that the distance that is 0.1 meters. That's given as the radius of the wheel. Okay. We need to think of then the force that this weight would provide perpendicular to the wheel itself. And so again, as we fill this in and kind of draw our triangle to figure out this perpendicular force that is provided by weight, okay, we know that the 45 degrees that this hangs at from the wheel will be represented on that angle of the triangle. We know that the right side of that triangle is equal to the weight, which is 1 kilogram and is the mass. So I just take 1 kilogram times 9.8 to get that weight. So the weight is equal to 9.8 newtons. To figure out my perpendicular weight then, I'll simply use the cosine of 45 degrees is going to be equal to my perpendicular weight divided by 9.8 newtons. Okay, just taking the opposite, or the adjacent side divided by the hypotenuse. Calculating that out for the perpendicular weight, we get a value of 6.93 newtons.
Okay, now that we have the perpendicular component of that force, we're ready to find the torque exerted by that 1 kilogram mass. And again, torque is equal to the force multiplied times the lever arm. The perpendicular component was 6.93 newtons. And our lever arm in this case is 0.1 meters. And that ends up with a total torque of 0.693 Newton meters. And again, for this particular side, that torque would then be in the clockwise direction. Next, we'll be looking at the torque exerted over here. This is the torque exerted in the counterclockwise direction by the 0.5 kilogram mass. And notice that it is already attached perpendicular to the lever arm. So since force pulls straight down, our lever arm at this point is horizontal. We don't have to do any additional work to figure out the force component then. So our torque would simply be the force multiplied by the lever arm. The force for this particular mass would be 0.5 kilograms times gravity. And again, our lever arm being 0.1 meters, and we get the torque in this direction of 0.49 Newton meters. So we have a total of 0.49 Newton meters being exerted in the counterclockwise direction, and we have a value of 0.693 Newton meters in the clockwise direction. Our net torque then is just found by taking the difference of those two, and we end up with a torque of approximately 0.2 Newton meters, and that torque then is in the clockwise direction. Okay, your Sioux Falls physics teachers here today to talk about a problem with torque and static equilibrium. We have some information here about a construction worker that is on a beam. It is also connected by a cable that is at an angle of 50 degrees. And our calculations are to calculate the tension in the wire and the components of the reaction force at the hinge. So the first thing that we'll want to do in this case is to make a rather detailed free body diagram. And remember that when we're dealing with static equilibrium and specifically torque, that in addition to the free body diagram, we also want to include distances for each of the forces that are applied. So we have our little diagram here to the right. We'll start with the beam. And notice first of all that it gives us the weight of the construction worker as 680 newtons. And then later our calculations are to occur when that worker is 2 meters out on the beam. So first of all, we want to identify where our hinge is going to be, our axes. And that would be right here at the end where that beam is connected to the wall. And at this point in time, then, he is a distance of 2 meters away. So in addition to having this force, which has a weight amount of 680 newtons, we also want to include the fact that that is a distance of 2 meters from the hinge. Now, the other piece of information that we have is his tool belt, which weighs 60 newtons. And we also know that the tool belt is out at the end of the beam, and the beam is 10 meters long. So we now have a force over here, which is another weight, 60 newtons this time. And the distance for that particular force is going to be the full distance of the beam, which is 10 meters. Finally, we have the weight of the beam itself. It says that the beam is uniform, so by that we can assume that it's a uniform density. So that means that the weight of the beam could be considered to be concentrated at a point in the center. When we add the weight of the beam, which is 450 newtons, the distance that we will put down in addition to that will be the distance of half of the length of the beam. In other words, we would have a total of 5 meters. We'll assume then that the weight of the beam could be considered as being centered in the middle of the beam. Now notice that those occur for all of the weights. However, we also need to put down the forces that will be in the upwards direction, and the first important one of these is the tension of the wire itself. So here, directed at an angle of 50 degrees, we would have the overall tension of the wire, and in addition to that then, since it is at an angle, we would want to break that down into components. So we will have a TX components of that wire pulling in the horizontal direction, and we'll have a TY component of that wire pulling in the vertical direction. Now finally, we also need to include, it talks about the components of the reaction force at the hinge. And again, remember that at this point we may not have much information about what those components are, but we can probably assume that there will be one component in the vertical direction, so that will be RY, and another component in the horizontal direction, RX. And those are both located at the axes of the hinge. Okay, now that we have this very detailed free body diagram of our situation, now we can start looking at what makes static equilibrium. Remember that there are really 3 conditions that we will be looking at. 1, to show that the object is not going to rotate, we must say that the sum of the torques is 0. So any torque pulling in the clockwise direction must be canceled out by a torque pulling in the counterclockwise direction. That will prevent our beam from rotating. The second 2 conditions involve the forces. All of the forces in the vertical direction must be 0. That will prevent any movement up and down. And all of the forces in the X direction, or the horizontal direction, must be 0, and that will prevent any movement left and right. Now again, we're going to be writing equations for all 3 of these, but usually we find that when distances are included, the torque equation is really probably the simplest one to start out with. So we're ready to write an equation now for our torques. To do that, we're going to consider any force that has a lever arm that is not zero, that is also perpendicular to the lever arm. So we're going to start with our weight values. As you can see here, we have 3 different weights. All of them are pulling in the downwards direction. So if we look at our lever arm here, all weight values would be perpendicular. And if our hinge is out here at the end of the beam, then all of our weights also have a lever arm distance that is non-zero. So for our torque equation, we will start by writing the torque of each of these 3 weights, which is pulling the beam downwards. And we can kind of see that if our hinge is up here, the weight then would be something that would pull it in the clockwise direction. So to calculate torque then, we need force times distance. So those that are pulling in the clockwise direction would be the weight of the man multiplied times the distance. We would find the torque from the beam by doing the weight of the beam times that distance. And we would find the torque from the tool belt by taking that weight multiplied by that distance. Now all of those would be things that would be pulling again in the clockwise direction. So all of those weights again are pulling this way right here. Notice that if we look at the forces that are perpendicular and pulling upwards in this direction, we have only the Ry and the Ty. But also notice that Ry is exerted at the hinge, so it does not provide any torque. So the only torque in the upwards direction will be provided by the Ty component. So Ty multiplied times the distance at which it is exerted, that torque needs to completely cancel out all of these other 3 torques put together. So now we're ready to add in numbers. 680 newtons and 2 meters for the man, 450 newtons and 5 meters for the beam, and 60 newtons and 10 meters for the tool belt. That is then equal to our unknown Ty multiplied times the distance to where Ty is attached, and that would be 10 meters. Solving for Ty, we get a Ty value of 421 newtons. So up here we now know 421 newtons is the vertical component of the tension in the wire. The next part of this then would be to find the Tx. And since they've given us the angle here at 50 degrees, this is basically just a trig problem. We have the value for Ty, and so we can write that the tangent of our 50-degree angle is equal to the Ty component, opposite side, divided by the Tx component, which is the adjacent side. And so tangent of 50 degrees is equal to 421 newtons divided by Tx. Using that trig then, we can find that the Tx value is 353 newtons. Continuing on with the Pythagorean theorem then, to find the overall tension, we can use the Tx and Ty values squared. We now have Tx as being 353 newtons. Ty was 421 newtons. And so solving for our overall tension, we have 550 newtons of tension in the wire. So we have successfully answered this question here. Calculate the tension in the wire. Now, once we have the components of tension, Then we can use our other two statements over here, so our vertical forces and horizontal forces, to find the components of the reaction force. We'll start with the vertical direction. So we know that the sum of the forces in the vertical direction must be 0. And as we can see from our diagram, again, we have the 3 weights pulling downwards. We have 2 forces pushing upwards. The component of tension, Ty here, is pushing up, and the component of the reaction force. So in this case then, if we add our 3 forces downwards, we have 680, 450, and 60 newtons. That sum must cancel out our total between the tension upwards, which is 421, and the vertical component of the reaction force. And if we complete the algebra on that, we find that the vertical component then must be 769 newtons as the vertical part of the reaction force helping to push upwards. And finally, we can use our last statement over here. The x components must also cancel out to find the horizontal components of R. Notice that there are only 2 horizontal forces. There's the R component in the horizontal direction and the tension component in the horizontal direction. Earlier we found that the horizontal tension was equal to 353 newtons. In order for the sum of our horizontal forces to be 0, the horizontal component of R must be equal in magnitude to that horizontal tension. So then we can say that the horizontal component of R is also 353 newtons. And notice that that would then be to the right, which cancels out the 353 newtons that are provided by tension pulling to the left. So our final answers then, tension in the wire is here, 550 newtons as the resultant between Tx and Ty. Components of the reaction force, we have R sub y, 769 newtons, and that would be upwards. And finally, we have R sub x, 353 newtons, and that would be to the right.